New Directions in Social Sciences. This is the first in a series of programs prepared by the listener-sponsored station, KPFA in Berkeley, California, for distribution through the National Association of Educational Broadcasters. These talks, delivered before the annual convention of the American Psychological Association in San Francisco, point to new developments in man's exploration of himself and the world he lives in. The keynote address was made by Dr. J. Robert Oppenheimer, director of the Institute of Advanced Studies at Princeton. He took as his subject, Analogy in Science. Dr. Oppenheimer.
I know that it is a terrible bear trap to talk the philosophy of science, and only in a very, very limited sense am I going to do that. One would think that the two sciences could hardly be further apart. In all hierarchical schemes, they are put far apart. Psychology, to everyone who works in the field, is felt to be a new subject in which real progress and real objectivity are recent. Physics is perhaps as old as the sciences come. Physics is reputed to have a large, coherent, connected corpus of certitude. This does not exist in psychology, and only the beginnings of it, the beginnings of things that are going to be tied together, are now before us. But I have always had a feeling that there were ways in which the two sciences had a community. Of course, all sciences do. One very simple one is that each is responsive to a primitive, permanent, pervasive human curiosity. What material bodies are and how they behave on the one hand, and how people, and the people-like animals, behave and feel and think and learn. These are the curiosities of common life, and they'll never be abated. Both for this reason can hardly make important pronouncements of a technical sort, which do not appear to have some bearing on our views of reality, on metaphysics. Both manifestly have and continue to have a fresh and inspiriting effect on the theory of knowledge, on epistemology. There are other ways in which we are brothers. In the last 10 years, the physicists have been extraordinarily noisy about the immense powers which, largely through their efforts, but through other efforts as well, have come into the possession of man. Powers notably and strikingly for very large scale and dreadful destruction. And we have spoken of our responsibilities and of our obligations to society in terms that sound to me very adolescent, because the psychologist can hardly do anything without realizing that for him the acquisition of knowledge opens up the most terrifying prospects of controlling what people do and how they think and how they behave and how they feel. This is true for all of you who are engaged in practice. And as the corpus of psychology gains in certitude and subtlety and skill, I can see that the physicist's pleas that what he discovered be used with humanity and be used wisely will seem rather trivial compared to those pleas which you will have to make and to which you will have to be responsive. The point, of course, is that as the relevance of what we find to human welfare and human destiny becomes sharper and more manifest, our responsibilities for explication, for explanation, for communication, for teaching, our responsibilities for being sure that we are understood grow. Not our responsibilities for making decisions, but our responsibilities for laying in a responsible way the basis of those decisions. There are other ways in which we are alike. The practical usefulness which our professions have gives us often the impression that we are liked for the wrong reasons, and that our true nature is very different from our public presence. We are both faced with the problem of the need to keep intact the purity of academic and abstract research, and at the same time to nourish and be nourished by practice. In physics, of course, our debt to technology, to engineering, is unlimited. I think it will be so in psychology as well. But there is no doubt that in our present state, we have parallel tensions. Both sciences, all sciences, arise through refinements, corrections, and adaptations of common sense. There are no unique, simple scientific methods that one can prescribe, but there are certainly traits that any science must have before it pretends to be one. One is the quest for objectivity, and that, I think, I mean not in a metaphysical sense, I mean in a very practical sense. The quest to be sure that we understand one another and that all qualified practitioners mean essentially the same thing. Common sense language is inherently ambiguous. When the poet uses it, or the rhetorician, he exploits the ambiguity. And when we talk in ordinary life, we almost need the ambiguity in order to get by. But in science, you try to get rid of that. You try to talk in such simple terms and match your talk with deeds in such a way that we may differ as to facts, but when we can resolve the differences. And this is, of course, the first step in the quest for certitude. But certitude is not the whole story. When you move from common sense into scientific things, you also move toward generality, using analysis, using observation, and in the end using experiment. And you do something which is even more, I think, characteristic. You look for novelty. You look for transcendence. That is, you look for features of experience that are not available in ordinary life. Characteristic in physics are the instruments that enable us to transcend elementary daily experience. The telescope that lets you look into the sky, today the enormous accelerators, which are in fact the logical extension of the microscope that enables you to look finer and finer into the structure of matter. I would like to be cautious in the parallels in psychology, but certainly the use of hypnosis, the use of drugs, are typical extensions into unfamiliar realms of human experience, which just bring out characteristics of psychological phenomena that are too lost in the day-to-day experience. There is an example which is a physicist's idea of a perfect experiment. It is the work that was done in McGill in the last years on, and I'm sure you have discussed it, on the effects of reducing sensory stimuli. Very simple arrangements to change the level of stimulation. And these produce evocative and, I would say, almost frighteningly great changes in memory, in the intellectual and cognitive life of the people who undergo them. Well, this is again an example of carrying to an extreme something which is encountered in ordinary experience, but which only the patience and the abstractness of experimental inquiry is likely to realize. We come from common sense, we work for a long time, then we give back to common sense refined, original, and strange notions, some of which I want to talk about today, and enrich what men know and how they live. And there, I suppose, the real hero is the teacher. I chose as my theme analogy in science. Really what I'm going to talk about is analogy as an instrument in science, and to a much lesser extent, some slight traits of analogies between the sciences. Mostly, this second theme has led to misunderstanding and limitation. But as for the first, analogy is an indispensable and inevitable tool for scientific progress. And I perhaps had better say what I mean by it. I don't mean metaphor, I don't mean allegory, I don't even mean similarity, but I mean a special kind of similarity, which is a similarity of structure, a similarity of form, a similarity of constellation between two sets of particulars, two sets of circumstances that are manifestly very different, but have this structural parallelism. It has to do with relation and interconnection. I'd like to quote you a scholastic comment on analogy. It's a translation of Penido. In a very general sense, every analogy presupposes two ontological conditions. One, a plurality of real beings, and thus among them, an essential diversity. Monism is the born enemy of analogy. And two, at the very heart of this multiplicity, of this inequality, a certain unity. It is a matter which we could argue as to whether these structural elements are invented by us or whether they're discovered in the world. I find it very artificial to say that they are invented, and mean by that they are more artifact than the particulars which they unite and describe. I may tell one incident in the long history of astronomy and physics, which makes this very vivid for me. For practical purposes, for prophecy and ritual, the Babylonians worked out a method of predicting what days the moon would first be visible, and lunar eclipses and certain rarer astronomical events. They did this by purely mathematical methods. They observed when the things happened and they got the pattern on it. It's something that you might recognize as harmonic analysis. And they were very good. They got so good that their methods were in use last century in India, and the people were predicting eclipses within 30 minutes, which is not bad at all, using these 2,000-year-old methods. They not only got very good, but they enjoyed it very much, and they did it for fun. Long after the practical reasons had gone away, they published these tables, apparently as we publish articles on the internal constitution of the stars, because it's interesting. They did all of this without any celestial mechanics, without any geometry. Nothing moved. There were no objects circulating around in orbits. There were no laws of motion. This was just from the feel of the numbers. Well, you know how today we predict eclipses and first risings. It would seem to me very wrong to pretend that the mathematical regularities which were the basis of the Babylonian predictions were something they invented. It would seem to me equally wrong not to recognize in celestial mechanics as we now know it, a far deeper and more comprehensive description of regularities in the physical world. And I think not only because it's a little more useful, I think that not only because it unites more subjects, but because it reveals an aspect of the regularities of the world which was wholly lost to the Babylonians. But whether or not we talk of this as discovery or as invention, analogy is an inevitable human thing, because we come to new things in science with what equipment we have, which is how we've learned to think, and above all, how we've learned to think about the relatedness of things. We can't, coming into something new, deal with it except on the basis of the familiar and the old-fashioned. The conservatism of scientific inquiry is not an arbitrary thing. It is the freight with which we operate. It is the only equipment we have. We can't learn to be surprised or astonished at something unless we have a view of how it ought to be, and that is almost certainly an analogy. We can't learn that we've made a mistake unless we can make a mistake, and our mistake almost always is in the form of an analogy to some other piece of experience. I'm not trying to say that analogy is the criterion of truth. You can never establish that a theory is right by saying that it's like some other theory that's right. The criterion of truth must come from analysis and confrontation with experience, and from that very special kind of objectivity which characterizes science, namely that we're quite sure we understand one another and that we can check up on one another. But truth is not the whole thing. Certitude is not the whole thing in science. Science is an immensely creative and organizing and enriching experience, and it's full of new things. And it is in order to get to these that analogy is an indispensable instrument. Even analysis, even the ability to plan experiments, even the ability to sort things out and take them apart, presupposes a good deal of structure, and that structure is characteristically an analogical one. I'm not pulling a political stunt. I want to read you now just a few words which William James wrote, which say this awfully well. He wrote them in one of his later accounts of pragmatism at a time when his own good sense and shrewd observation and wisdom and humanity made him aware of the fact that just to say that an idea was true because it worked was a rather poor description of what went on in science, and that something was missing from that account. This is what he wrote. The point I now urge you to observe particularly is the part played by the older truths. Failure to take account of it is the source of much of the unjust criticism leveled against pragmatism. Their influence is absolutely controlling. Loyalty to them is the first principle. In most cases, it is the only principle. For by far the most usual way of handling phenomena so novel that they would make for a serious rearrangement of our preconception is to ignore them altogether, or to abuse those who bear witness for them. This for the conservatism and the inevitability of starting out when you're talking about new things by supposing that you have seen them before, and then finding out in sharp, precise, and one hopes synoptic ways where the mistake was in the analogy and what has to be set right about it. I'll read you one other thing. This is from Charles Peirce, and then I'll get on with my talk. Peirce is also talking pragmatism, and he comes awfully close to what we have been talking about. And then he says, however, as metaphysics is a subject much more curious than useful, the knowledge of which, like that of a sunken reef, serves chiefly to enable us to keep clear of it, I will not trouble the reader with any more ontology at the moment. What I want to do next is to give you 5 examples of the use of analogy in atomic physics. They will not all be equally familiar. Perhaps that's an overstatement. Some are very new, and even to the point new that I don't know how good the analogies are, and we haven't yet found all the decisive point at which they're misleading. The analogies in physics may very well be misleading for biologists, psychologists, because of the enormous part that rather rigid formal structure plays in physics. Not necessarily quantitative, though much of it is quantitative, but our ability to write down synoptic relations in symbolic form, our use of shorthand, enables us to talk of vast amounts of experience, very varied experience, very detailed experience, in a shorthand way, and to point to mistakes so that you only erase one letter and everything is changed entirely. And that can be a little bit misleading. This is not meant as a paradigm, but nevertheless as an illustration of the fact that in what is regarded as the most rigorous and certain of the sciences, we use an instrument which has been in great disrepute because uncritically used, it can confuse invention with confirmation and truth. I'd like to give a first example, which is not from atomic physics, which is almost from pre-physics, because it deals with things that are very familiar and yet illustrates the nature of the role of form in the use of analogy in physics. This has to do with Jean Buridan and the Paris school in the 14th century. The classic view, and physics has a special meaning for the word classic. Classic means wrong, but it means the wrong view that was held to be right a little while ago. The classic view was that the natural state of matter was rest, and that where you found bodies moving around, you needed to look for a cause, and this cause was a force. And this was the schoolman's view, it was Aristotle's view. It is in fact supported by an awful lot of observation. It was not well supported by the observation on projectiles. The notion that the air behind a bullet pushed the bullet became less plausible the more you watched the bullet. And Buridan and his many anonymous thinkers took a step which was to make a new analogy, and which probably was the greatest step in the history of Western science. They said, it is true that matter has a natural state, but it is not rest. It is true that when it departs from this natural state, it can be ascribed to the intervention of a force. But the natural state is one of constant impetus, one of constant momentum, one of uniform velocity. And with that, the beginnings of rational mechanics and of rational physical science were made. What do you do? Well, there isn't a blackboard here, but if there were, you simply replace the coordinate by the velocity. It is a small change, and yet it's the change in the whole way of thinking about the physical world. Well, my 5 illustrations from atomic physics, I will mention what they are. They are what has happened to the idea of waves, what has happened to the idea of classical physics in the atomic domain, the so-called correspondence principle, the analog between radioactive decay and the emission of light, which we owe to Fermi, the analog between electromagnetic phenomena and forces and nuclear forces, between electrodynamics and mesodynamics, and a final subject, which I will only call strangeness, because that's about all I know about it. Well, take the wave business. It originated, of course, in the observation of regular rhythmic changes in matter, waves on water, and was followed by an easily conducted physical exploration of sound waves, where there is a periodic change, a regular change in the density of air or whatever the sound is passing through. Both of these phenomena exhibit a characteristic. If two waves collide, they can cancel each other out, and they can reinforce each other. They show interference. They have another abstract property. If you put waves through an orifice or around an obstacle that is small compared to the wave, then the obstacle or the orifice doesn't cast a sharp shadow, but there are all kinds of interference effects which are called diffraction. Waves superpose. If you have two, the sum of the two waves is just what you get by adding algebraically and not arithmetically. You get a zero if you add a positive and negative, which is the interference. And this is the abstract set of properties which is persistent. Because light is also a wave motion, but there is no matter in motion. There is no substrate. It was for a long time thought there was, and it was a great sign of progress in the 19th century to get rid of that. What is in motion are themselves physically measurable things, but rather abstract things, electric fields and magnetic fields. But again, interference, diffraction, and superposition, the same abstract characteristics, and again, in principle, the infinitely regular, infinitely repeated pattern as a special case of a wave. And the most extreme examples are the waves of atomic mechanics, of wave mechanics, because these waves, in the first place, are in multidimensional space. They are represented by complex numbers, so there are not even things that you could measure and get an answer to, and they are quite unobservable. There is nothing to measure in the physical world that corresponds to these waves. They are connected with observation, but they have again these same abstract properties: interference, linearity, superposition. And one talks about them, one uses much the same mathematics, although it is not the fact that one can use the mathematics, but the fact that the structure and the relations are the same that is the decisive discovery, and then it is natural to use the mathematics. These waves, they represent, if one wants to say what they are, not matter, not forces, not electric fields. They represent essentially a state of information about an atomic system. But at each point, the first workers have tried to make the theory like the earlier theory. Light like sound as a material wave, matter waves like light waves, like a real physical wave. And in each case it's been found that one had to widen the business a little bit and find the disanalogy which enabled one to preserve what was right about the analogy. The second example is a massive one. It is, I think, the greatest experience in this century for the physicists, even greater than relativity, and that is the discovery of atomic mechanics. And here again, in a sense very characteristic of scientific theory, an enormous conservatism presided over and guided the development and has given it shape. Well, what is all this about? When one gets to the atomic domain, and this is a domain of small actions, of limited distances and limited impulses, of things such as you encounter in atoms and nuclei, then the coarseness of the whole physical universe, its granular or atomic structure, for the first time begins to manifest itself. Not the granulation of the fundamental particles, but the granulation of atomic physics itself, of the quantum of action. And what this means is that when you're trying to study such a system, there are aspects of it which are accessible to experiment, but are not compatibly or simultaneously accessible to experiment. The famous example is in the uncertainty relations, that you can study this location of something in time and space. But if you do that, you use an experimental setup which makes it impossible to know exactly what the impulse or velocity or energy of the system is. Or you can do the opposite. You can study the impulse, but then you lose account of where it is. And you can, of course, compromise, but you cannot combine. And one calls these the complementary aspects, complementary character of the fundamental observations. And that means that you can't talk about an atom as you can about a classical mechanical system. You can't say the objects in it are here and they're moving in certain orbits and so on. In fact, in ordinary atoms, there are no orbits. In atoms as they're ordinarily encountered, there's something entirely different. Stationary states, which have a stability, a uniqueness, a reproducibility, which has no counterpart in classical physics at all, which couldn't exist if it were not for this revolutionary new feature. And one can talk about these stationary states. One can describe them accurately, but one has a whole change from the familiar experience of bodies in motion, of matter in motion. Sometimes people say that this atomic theory is characterized by the fact that you can't observe a system without disturbing it. But that's not quite right. It isn't the disturbance which makes the trouble. It's the fact that the means of observation would be frustrated as means of observation if you tried to take an account of the disturbance that you are making. It's a slightly more subtle point. Sometimes people say that the electron has a position and momentum, but you can't measure them simultaneously. But this isn't right either, because only the act of observation, the coupling of the atom with the physical measuring equipment, makes it logically permissible to attribute a position to an electron. You can't get the right answer by saying, well, it has a position, I don't know what it is, let me average. If you do that, you get a wrong answer. You have to admit that unless the situation is one which is created by your physical operations on the atomic system to realize, to manifest, to objectify the localization of the electron, then it won't be localized. It will have no properties at all, apart from what you do to it. Well, all of this is so extraordinarily radical and so extraordinarily unlike Newtonian mechanics. But what does the physicist say? Even before the full answer was found, it was said, there is something going on here which limits classical ideas. They don't quite apply. But in any situation to which they do apply, we know they're right. And therefore, whatever laws hold in the atomic domain, they must merge into the laws of classical mechanics. There must be a one-to-one correspondence, an analogy there. Otherwise, in capturing some insight into this new domain, we'll throw out all we ever knew and throw out things that are true. This was called the correspondence principle, and a sample of how extreme this correction of the analogy, which has revolutionized everything, how extreme that is in a highly formalized science, one can give as follows. Every law of classical mechanics is true in atomic mechanics, that the velocity is proportional to the momentum, that the change with time of the momentum is proportional to the force, that the energy is conserved, all of these things, provided you will make one formal change, provided you will say that the momentum and the coordinate are not numbers, but are objects such that when you multiply the momentum by the coordinate and you multiply the coordinate by the momentum, you don't get the same answer. The difference between these two is an imaginary universal atomic constant. If you just write that one formula, then everything you had before is formally identical. Well, this is as powerful an illustration of the use of analogy and disanalogy in a formal science as I know. I'm going to have to come back to other aspects of this great development. Let me run rather more briefly over the three other examples. Radioactive nuclei, all of those practically that are made artificially and many natural ones, disintegrate by sending out electrons. We puzzled and puzzled over it, and it was quite clear there were no electrons in nuclei. So Fermi made the suggestion that one might describe this as one describes the emission of light or light quanta from atoms. Nobody would say there was a light quantum in an atom, but still we observe the light coming out. And he made a theory along these lines. It wasn't exactly right. The analogy was not quite perfect, but with a very little adjustment, which took 15 years of comparison with details of experiment, we got a theory that works fine. Yukawa, the Japanese scientist Yukawa, had a somewhat braver analogy, and its fortunes are still not entirely resolved. The way in which one describes the forces between charged bodies is, of course, that one charged body makes electric fields, and these electric fields are propagated to the other and give it some momentum and push it around. Nuclear forces, which are not electromagnetic and are very strong and spectacular, Yukawa said would probably be due to a field of a new kind. And replacing the electric field, there would be this new field. Replacing the light quanta, there would be new kinds of particles. And using the general arguments of relativity and complementarity, quantum theory, he concluded that because the forces between nucleons are of short range, these particles would have a mass of a couple of hundred times that of the electron, and from other particularities of the nuclear force drew conclusions about the nature of these particles. Well, they were found. They're called mesons, and the analogy which Yukawa started with has been refined. One has discovered that there are many differences between mesodynamics and electrodynamics. One is at the present point not quite sure what all of the key points of difference, of disanalogy are. Some of them have been discovered, but they appear to be rather the more trivial ones. But the theory as it stands now has predictive value. It's brought order and clarity to a part, anyway, of nuclear physics. It has kept people busy on 20 years, not surely of treason, but of a very, very odd kind of rarefied boondoggling. It has been a very major event in physics, and I don't know at the moment how to describe what limits this analogy, why it isn't a perfect one. If we were having a seminar on physics, I would talk an hour about it, but I still wouldn't know. It is probably, though, connected with my fifth example. It's true that these mesons were discovered, but not very long after that, and perhaps it will continue, I don't know. And in the last 5 years, one has found a whole lot of other objects, about 6 manifestly different and maybe more, which are also quite stable and last quite a while, and which are not simple mesons of the kind Yukawa envisaged. Almost certainly, their intervention in the picture, which is not something that is provided for in the analogy we started for, will provide a clue to the new point. But their existence raised a different problem, because whenever in physics one encounters a situation in which something doesn't happen or happens very slowly, one finds it interesting. And the great point was, why do these new particles not decay quickly. They do decay, but it takes them a terrible long time, and they come apart into products which one would expect to have emerged right away. Well, we have a great deal of experience with reactions that occur slowly. And a characteristic reason for that is that something doesn't want to change, like the energy of a system or the total charge. Something is conserved. And whenever that turns up, it also turns up that the fact that something is invariant is mathematically identical with the statement. The fact that something doesn't want to change is mathematically identical with the statement that something makes no difference to the system, either its position in space or some quite abstract idea like that. So the first thing that we all did was to try to find the characteristic of these new particles that didn't want to change. That has not been hard to do, and a most successful theory which accounts for some of the great peculiarities in this field has been developed, but we haven't a good name for what doesn't like to change, and the inventor of it calls it the strangeness. Well, these 5 examples are not at all meant to exhaust, but merely to illustrate the powerful use, the inevitable use of analogy in a well-developed, in a highly organized, highly formalized, and highly coherent science. And I need to point out that in every case, an immense amount of experience, of measurement, of observation has gone in both to the correction of the analogies and to their confirmation. When I turn to the question of analogies between sciences, I talk of something very different. There is, first of all, the fact that there are often things which are not analogies at all. There are congruences when in 2 different sciences, by different techniques, different language, different concepts, it turns out that the same subject has been explored from 2 sides, and when it turns out that there is a mapping of one description on the other. Usually one description contains more elements than the other, is richer. The other may be more economical and more convenient. Examples, the chemical theory of valence and atomic physics, which are identical except that atomic physics does give an account of some phenomena, resonance and so, which were hard to cope with within the framework of the classical chemical theory. Another example, newer and perhaps not yet as well explored or understood, classical genetics on the one hand, and the discovery of the genetic substances, DNA and so, which are at the moment very close to being into a one-to-one correspondence, but with the certitude that the biochemical description is richer and has more dynamics in it and more subtlety in it. Well, it's not this that these are the great events of science, and when they happen in psychology, there is rejoicing, and when they don't happen, there is hope. These are the great events which bring coherence and order and large structure to the unfolding of scientific life. But probably between sciences of very different character, the direct formal analogies in their structure are not too likely to be helpful. Certainly what the pseudo-Newtonians did with sociology was a laughable affair, and similar things have been done with mechanical notions of how psychological phenomena are to be explained. I know that when physicists enter biology, their first ideas of how things work are indescribably naive and mechanical, and they are how things would work if the physicist were making them work, but not how they work in life. I know that when I hear the word field used in physics and in psychology, I have a nervousness that I can't entirely account for. And I think that especially when we compare subjects in which ideas of coding, of the transfer of information, or ideas of purpose are inherent and natural, with subjects in which these are not inherent and natural, the formal analogies have to be taken with very great caution. But for all of that, I would like to say something about what physics has to give back to common sense, that it seemed to have lost from it. Not because I am clear that these ideas are important tools in psychological research, but because it seems to me that the worst of all possible things would be if psychology were influenced in any way to model itself after a physics which isn't there anymore, which has been quite outdated. Now, one of the points, which is not the direct one. You see, we inherited at the beginning of this century a notion of the physical world as a causal one in which every event could be accounted for if we were ingenious, a world characterized by number, where everything interesting could be measured and quantified, a determinist world, a world in which there was no use for a room for individuality, in which the object of study was simply there, and how you studied it was a matter of your job, but it didn't affect the object, it didn't affect the kind of description you gave of it, in which the objectifiability went far beyond merely our own agreement on what we meant by words and what we were talking about, in which objectifiability was something you could do irrespective of any attempt to study the system you were talking about. It was just the given real object, there it was, and there was nothing for you to worry about of an epistemological character. Well, this extremely rigid picture left out a great deal, and it's of common sense. And this is one of the things that I want just to wind up with, because the whole business of science doesn't just lie in getting into realms which are unfamiliar in normal experience. There's an enormous work of analyzing, of recognizing similarities and analogies, of getting a feel of the landscape, an enormous qualitative sense of family relations, of taxonomy. It's not always tactful to try to quantify. It isn't always clear that by measurement one has defined something very much worth measuring. It is true that for the Babylonians it was worth measuring, noting the first appearances of the moon, because that had practical value. Their predictions, their prophesying, and their magic wouldn't work without it. And I know that many psychologists have the same kind of reason for wanting to measure. But it isn't, and it is a real property of the real world that you are measuring. But it is not necessarily the best way to advance the true understanding of what's going on. And I would make this very strong plea for pluralism in the kind of methods that in the necessarily early stages of sorting out an immensely vast experience may be fruitful and may be helpful, not for objectivity, that one has to agree on, and not for a quest for certitude which will never be quite adequately rewarded, but for the use of naturalistic methods, the use of descriptive methods. I have been immensely impressed by the work of one man who visited us last year at the Institute, and that's Jean Piaget. And when you look at it, really, his statistics consist of one or two cases. He has just a story, and yet I think he has added greatly to our understanding. It is not that I'm sure he's right, but he has given us something of which to inquire whether it is right. And I make this plea not to treat too harshly those who tell you a story having observed carefully, without having established that they are sure that the story is the whole story and the true story. But it is, of course, in that light that I look at the immense discipline of practice, that with all its pitfalls, with all the dangers that it gives to premature solutions, it does give an incredible amount of experience. Physics would not be where it is, psychology would not be where it is, if there were not a great many people willing to pay us for thinking and working. But now, as to this point about what physics had taken out of common sense, I don't know whether these will prove helpful, but at least it loosens the resources that one can bring to any science. What are these ideas? Well, in our natural unschooled talk, and above all in unschooled talk about psychological problems, we have 5 or 6 things which we have got back into physics with complete rigor, with complete objectivity in the sense that we understand one another, with a complete lack of ambiguity, and with a perfectly phenomenal technical success. One of them is just this notion that the physical world is not completely determinate. There are predictions you can make about it, but they are statistical, and any event has in it the nature of a surprise, of a miracle, of something that you could not figure out. Predictive, but within limits, and ordered, but not completely causal. And another of these ideas is the limits on how much we can objectify without reference to what we are really talking about in an operational, practical sense. We can say the electron has a certain charge, and we do not have to argue as to whether we're looking at it to say that. It always does. We can't say it has a place or a movement. If we say that, we imply something about what we ourselves, I don't mean as people, but as physicists, are doing about it. And a third is very closely related to this: the inseparability of what we are studying and the means that are used to study it, the organic connection of the object with the observer. Again, the observer, not in this case as a human, but in psychology, sometimes as a human. And then, as logical consequences of this, the idea of totality or wholeness. Newtonian physics, classical science, was differential. Anything that went on, you could break up into fine points and look at. If you look at an atomic phenomenon between the beginning and the end won't be there. It'll be a different phenomenon. Every pair of observations, you know this, you predict that, is a global thing, and it cannot be broken down. And finally, every atomic event is individual. It is not in its essentials reproducible. Well, this is quite a pack of ideas that we always use: individuality, wholeness, the subtle relations of what is seen with how it is seen, the indeterminacy and the acausality of experience. And I would only say, if a poor and limited science like physics could take all these away for 3 centuries and then give them back in 10 years, we had better say that all ideas that occur in common sense are fair as starting points, not guaranteed to work, but perfectly valid as the material of the analogies with which we start. If any of this is true, there is another thing that physicists and psychologists have in common, and that is we are going to have quite a complicated life. The plea for a plural approach to exploration, the plea for a minimal definition of objectivity that I have made, means that we are going to learn a terrible lot. There are going to be many different ways of talking about things. The range from almost ununderstood practice to recondite and abstract thought is going to be enormous. It means there are going to have to be a lot of psychologists, as there are getting to be a lot of physicists. When we work alone, trying to get something straight, it is right that we be lonely. And I think in the really decisive thoughts that advance the science, loneliness is an essential part. When we're trying to do something practical, it's nice to have an excess of talent, to have more sailors than are needed to sail the ship and more cooks than are needed to cook the meal. And the reason is that in this way, a certain elegance, a certain proper weighing of alternatives guides the execution of the practical task. It was that way during the war on many things, and it's, I know, a luxury that we all want. We are all, for all kinds of reasons, worrying about how our scientific community is to be nourished and enough people who are good enough come and work with us. And then on the other side, we're worried about how we're to continue to understand one another and not get totally frustrated by the complexity and immensity of our enterprises. I think there are good reasons of an inherent kind, as I've said, beside the competitive reasons with the communist world, why we would do well to have more and better scientists. I know that exhortation, money, patronage will do something about this. But I don't think that's all. I think that if we are to have some success, it must be because as a part of our culture, as something that is generally understood, the understanding, the life of the mind, the life of science, is something which in itself, as an end, as well as a means, is appreciated, is enjoyed, and is savored. I think that has to be a very much wider thing in the community as a whole, before we will enjoy with the community as a whole the healthy relations without which the developing powers of scientific understanding, prediction, and control are really monstrous dangers. It may not be so simple, this having in the community at large some genuine experience of the pleasures of understanding and discovery. It may not be simple because beyond that, what this requires is not merely that this is agreeable, but that it has a kind of virtue, and that not only the consideration of ends, of products and accomplishments and status, but the texture of life and its momentary beauty and its nobility are worth paying some attention to, and that among the things that contribute to that are the life of the mind and the life of science. Let's try.
The program you've just heard was produced by KPFA, the listener-sponsored station in Berkeley, California. It was one of a series called New Directions in Social Sciences.